Here's a quick introduction to matrices. It's our next topic. There's many cool things you can do with matrices. They're the heart of how people do linear algebra. It's a huge subject. But we're going to use them first just to streamline how we've been doing the process of elimination. So here's an example that we did of a 3x3 system. It was a little special because it had no x in here, and I'm going to put that in explicitly though as a 0x. And let me make it line up a little better. And we have this method that involves rewriting the system a few times. For a 3x3 system, we just need to usually write it 3 times. But for a 4x4 system, we'd have to rewrite it 4 times. That's a lot of work. We'd like to streamline that, and we'll see that it gets us a lot of other advantages. But what we're going to do is we're just going to write down the pattern of numbers in a grid, and it's called a matrix. And so we're just going to write down the coefficients in front of x, y, and z, and the constant. Coefficients in front of x, y, and z, and the constant. And it's absolutely essential that we have things lined up, x, y's, and z's. We don't write them in a different order with like x then z then y, or z then x then y. It's always written in the way we've been writing it. And we're basically just not writing the x's, y's, z's, and the equals. And so that's going to be a streamlined way to write things. So the correspondence here is that each row of a matrix, of this kind of matrix, which is called, let me say, specifically, this is called the augmented matrix of this system. Augmented means we're including the constants. Sometimes we actually just have these 3. I'll talk about that in a second. The augmented matrix, the correspondence is that each row corresponds to a separate equation. So a 3-equation system will have a 3-row matrix. Each of the columns corresponds to a separate variable. That's x, that's y, then z, except the rightmost column is the constants that we always put on the right-hand side. And if we only did this part of the matrix, let me copy and paste and modify this. If we only did, let's say this guy, without the constants, that is called the coefficient matrix, because it's just the coefficients. And we'll see that that has its own role to play. Right now, we're going to work with the augmented matrix, which encodes the entire system, including the right-hand side. So how does that work? Well, how does it streamline the process of elimination? It's just a little bit less writing for now, and then we'll see that it's get some other advantages. So we start out with this matrix. And then what was the first step we needed to do with that? It was a row exchange. And so this guy here, the difference between this matrix and this matrix is a row exchange. Or in other words, what we're doing is we're taking this system and we're just rewriting it in a different order. Okay? And so this is called a row exchange. This first row has ended up in the second row has ended up in the first row. I didn't change the third row. Then the real workhorse of elimination is, and then let's see, I think I just copied it here. Yeah, I haven't changed anything. The real workhorse of elimination is to produce a 0 here. Let's see how that works. Well, with equations, it would have been 2x minus 3y plus 2z equals 1, and the equation 5x minus 8y plus 7z equals 1. And we would have, let's say, multiplied this by 5 to get 10x minus 5y plus 10z equals 5. And multiply this by minus 2 to get minus 10 plus 16. Oops, that was a 15y. There we go. That's what's wrong. That was 10x minus 15y plus 10z. I just didn't do the 1. And then multiplying this by minus 2 minus 14z equals minus 3. There we go. Okay. So then we would add those equations and we would get y minus 4z equals 3. Okay. So how does that work in terms of matrices? Instead, it's just a little easier, just a little more streamlined. Let's just put in a single row matrix. And again, this is the scratch work over here on this side. It's not, you don't have to do as much scratch work as I'm showing. So we go ahead and multiply this first row by 5, and we just get exactly the coefficients that we wrote down before. It's just a little streamlined. And then we're going to take that. We're going to take the bottom row here, and we're going to multiply it by minus 2. Let's just clear this out. So we're multiplying this bottom row by minus 2, 16, minus 14, minus 2. And then we're just adding them together. So when we add them together, and we're going to put them in here. So we're going to get 10 minus 10 is 0, 16 minus 15 is 1, 10 minus 14 is minus 4, and 5 minus 2 is 3. And it's just, of course, encoding this equation, y minus 4z equals 3. So it's just a nice, quick way, relatively quick way, to do this process that we were doing already. Then the next one I'm going to show without even any scratch work because it's so simple in this particular case. If I just take the second equation, the second row minus the third row, I get 0, 0, 0, 5. Hey, that's interesting. That last equation, remember we can always take these matrices and put them back into equation form. If I just take the last equation and put it back in equation form, it's really 0x plus 0y plus 0z equals 5. That's 0 equals 5, that's impossible. So we discover that it's an inconsistent system. That's nice, because without even putting it back into equation form, we discover that. Usually when we back substitute, we actually go ahead and write down the equations. People find it usually easier that way, although we'll find an even more advanced method, which continues with the matrices more. But so right now, the first version of the matrices, we're just going to use it for the elimination step, and then we would convert it back to equations. But here it's kind of nice because we're done. We know it's an inconsistent system. Let me just give some terminology. These crucial operations where we play off the rows against each other, and it's corresponding to the crucial operation of when we wrote it as equations, those are called row replacement operations. So the three kinds of operations we're allowed to do are row switches, row exchanges, which I showed you up above, row replacement, which is add a multiple of one row to a multiple of another row, and then if we need to, we can just plain multiply a row by a non-zero number and leave it in place. And that's often useful for convenience, and we'll see that we'll have a really big use for that soon enough. Okay, so you can look in your book for their version of this as well, but I just figured it was good to show an example of how matrices are going to work for us at the very start.